Start recording. There we go. Because you will come across them possibly on your test, certainly maybe on the AP exam, and you don't want to be like flummoxed by it. You don't want to be like, where's my salt bridge, right? Because if you look at this thing, you're like, there is no salt bridge. There's not even two beakers, except for there kind of are, okay? So what you have is you have a container of some kind, and in the middle of that container is a porous membrane, okay, or a porous barrier. And if that is the case, then you can have cations and anions move from one side to the other side. And why do cations and anions move? Tell your partner. Why do they need to move? To maintain electrical neutrality, okay? So you're not going to have to draw one with a porous barrier or anything like that, but you should be aware that they exist. And so, you can be like, all right, I'm not weirded out by that. I know that they happen. We can also have, sometimes they have a sort of little two beaker system. This is kind of a specialized little piece of glassware here where you've got two beakers actually connected by a tube of glass. And in that tube of glass is a porous disc which serves the same function as the porous membrane. Make sense? Okay, cool. What else have we got? Sometimes if you're like, I do not have the fancy little YouTube, to make a salt bridge, you can actually just use a strip of filter paper that's been soaked in whatever thing you have. You'd probably want it to be fairly thick so that it's not going to dry out, right, over the course of however long you're doing it. But yeah, and the ions will move through there just like they would through a regular salt bridge. Okay? Do we have any others or is that it? Let's check. Ooh, and then here's a fun one. We have a porous cup. So maybe it's made of, I don't even know what you would make this out of, maybe some sort of ceramic or something like that, where it's got tiny little holes in it. You know what I mean? It's kind of I don't know, I'm trying to think of something that's kind of like sandstone, but not really like sandstone, where it's got little particles that are stuck together, but there's little pores in it. Yeah, except for the holes are not that big. Okay, tiny. So ions can move through, but the water's not going to be gush. Do you know what I mean? And they'll move fairly slowly from one to the other. So it's just like having two beakers, except for one beaker is completely porous. So ions can move. Is good? Okay. Cell notation. Shall we take a look at the little video? Did you watch the video on cell notation? Anybody? One person, two people. Okay. Well, actually, you know what? We can go to the next page. We can go to the next one. We can go to 6.3c, which is on page 82. Because in AP, you will see cell notation, okay, for sure. And in cell notation, a vertical line represents a phase boundary. What is a phase? Do you remember this from the kinetics unit, the reaction kinetics unit, where we had homogeneous reactions where everything was all in the same phase, and heterogeneous reactions where you had different phases? Yeah? So if we were to look at our electrochemical cell or our galvanic cell, this copper anode is a copper solid phase. Yes? This here is an aqueous phase. So when we're going to make a notation for this cell, rather than writing out the entire copper anode and then drawing out the whole beaker and filling it with solution, what we can do is we can just write copper solid as our first phase. And then we're going to draw our vertical line. Okay, that is our phase boundary. And then our other phase, we don't worry about the nitrate ion. We only write down the ion of interest. Okay, so we don't care about the nitrate. We only care about the copper 2+. Does that make sense? Okay. So we would have our aqueous phase here. There we go. Now, a double line, a double vertical line stands for the salt bridge. Or if you have a porous barrier or a piece of filter paper or a porous cup, that's the double lines. Okay, it's whatever the ions are passing through. So those are your double lines. That is your, that is your salt bridge. And then on the other side, we have our aqueous phase. Okay, again, we've got our aqueous phase. The silver ions are the ions of interest. There is a phase boundary between that and the silver solid. So far, so good? So this little notation here takes the place of that entire drawing. Isn't that nice? Maybe. Maybe it's nice. I don't know. It just makes it a lot simpler. We don't include spectator ions. We do not include coefficients. When we are given initial concentrations of the ions, they are usually included in the cell notation. So if we were told that copper 2+ was 1 molar, we would include that 1 molar, and we include the states. Okay, so we make sure we've got our solid, aqueous, aqueous, solid. Now, how do we know what order to put them in? Right? Do I put the copper on the left or do I put the silver on the left? Well, I'm hoping it's going to tell us on the next page. Let's go see. Oh, no, it actually tells us here. The order of substances is anode, anode solution, cathode solution, cathode. Okay? So it is in alphabetical order. It's also the order in which electrons flow. So electrons are going to flow from the left one to the right one. Oh, I need to fix that. That should be a capital. And sometimes people call this an ion sandwich because what ends up being in the middle are the ions. So the electrodes go on the outside, with the ion sandwich, the ions in the middle, in between them. So that's the order you put them in. It's going to be always the anode over here and the cathode on the right. Is good? Okay, and that is probably all you need to know about cell notation. Okay, we're going to take just a very, very quick look at what comes next, just in case I've missed something here. Yeah, here we go. Okay, so some redox reactions involve species that are poor conductors of electricity, such as gases. Can you imagine a gas conducting electricity? Right? That's not going to happen. So if you have a copper electrode, obviously the copper can lose electrons. But if you have a hydrogen electrode, the hydrogen can, oh, I'm saying it wrong. Never mind. Let's just read it through because, okay. We're going to read it because I'm going to make a mess of it otherwise, because I only teach this once every 2 years, so it's not like in my normal pattern. Okay, so what we do in instances like that is we can have an inert electrode. What does inert mean? Inert means unreactive. And some things that are unreactive, platinum, all right, and also graphite. Why is platinum unreactive? I just know that it is. Let's go look. Platinum. Is it on here? It's not even on here. Okay, hang on. Let's go look up the platinum reactivity. Or you can just believe me. Sure. Yeah? Okay, cool. Because it's not actually that important as to why, for the grand scheme of things. And we're sort of pressed for time, so let's just go with that. Now, the thing about both platinum and graphite is they both conduct electricity, so the electrons can flow through them. They both conduct electrons, but neither will gain electrons or lose electrons. Do you guys remember why graphite is conductive? Yeah. It is a covalent network, okay? And they're in sheets. Yes, absolutely. So we have carbon, which is in sheets like this. Yes. And what shape do the carbons make when they are attached to one another? They make a hexagon. Yes? So at each corner of these hexagons is a carbon atom. So if this is a carbon right there, how many bonds does it have? It has 4 bonds. But why do I only see 3? There's one that's keeps going around. Yeah, so what we have is we have alternating, right? I think I've done this wrong here. Have I done it wrong? Anyway, you end up with resonance. The 4th bond. Oh, so first of all, actually, before we go into the 4th bond, what is the hybridization of carbon here? sp2, because remember, you just count up the areas of electrons, right? You count up the electron domains. There's 3 electron domains. And an electron domain can either be a bond or a lone pair. In this case, we don't have any lone pairs. And then you say S, P, P, that's 3, sp2. Yes? Okay, so that's sp2 hybridized. And what shape is this? Almost triangular, but not quite triangular. Trigonal, planar. Pyramidal would be like this, where you have a lone pair up on the top. Yeah, pushing those other electrons away. Okay, so that's just a little quick review. How many sigma bonds on this carbon? Yep. Because remember, every single bond is a sigma bond, and every first bond of a double or triple bond is a sigma bond. Say the first bond of any bond is a sigma bond. So sigma, there's only one bond, so they're all sigma. In a double bond, you have a sigma bond, and then you have a pi bond. And in a triple bond, you have a sigma bond, and then you have a pi bond and another pi bond. Okay, so and it is these delocalized electrons. So this is a delocalized pi bond. So we have one pi bond, which is delocalized. And it is those delocalized pi bonds can flow across the sheet. They're above and below the sheet. Yeah? Yes? And we actually call a sheet of graphite graphene. Okay, so a single sheet is called graphene. I don't know that that's important though, okay? The important part is that you've got those delocalized electrons above and below, because if you have a pi bond, you've got your carbons here, yes, and you have your sigma bond with the electron density along the, what do we call that thing here? That is called the okay, inter means between. What's it between? No, it's not intermolecular. I've got a carbon bonded to a carbon. What's in the middle of each carbon atom? In the middle of each carbon atom. The nucleus, the internuclear axis. Do you remember that? The internuclear axis, okay? So there is our sigma bond where the electron density is along the internuclear axis. So a sigma bond, electron density is along the internuclear axis. And when we have our pi bond, where is the electron density? When you have a sigma bond, it is end-on overlap. Do you guys remember that? So if you have two s orbitals, you end up with a single bond, a sigma bond. If you have a p orbital and a p orbital, that is also a sigma bond. But what if my p orbitals overlap this way? Where is the electron density going to be relative to the nuclei? The electron density is going to be above and below. Not just one, it's going to be above and below. So this is just one bond. I wanted to say this is a single bond, but it's not a single bond. It's the second bond of a double bond, but it's only one bond, but the electron density is above and below. So this overlapping bit here, we would have those two lobes together make a pi bond, one pi bond. So that sigma bond with that pi bond makes a double bond. And that's why when I talk about the electron density being above and below the sheet, this bond here is that sigma bond, and that is along the internuclear axis. It's in between the two nuclei, the nucleus of this carbon and that carbon. The other pi bonds are going to be kind of floating up here or back here. Does that make sense? So they're kind of like in a little ring shape above each hexagon. And then they can move from one hexagon to the other hexagon. Okay, because those delocalized electrons can move. How do we feel about that? Does that ring bells? We kind of remember it? Are we thinking maybe we need to study if we're going to be writing that AP exam in May? Yeah, okay. I will be giving you stuff. Remember what this felt like when you're looking at it and you're like, oh, I don't want to do that now. It's not till May. Remember how this felt. Like, take a moment, close your eyes. Close your eyes. Take a moment. Remember how disorienting this felt, perhaps? Where you're like, oh, yeah, I did not remember that at all. And just imagine feeling like this on April the 20th, when you have only 10 days left before your exam. Can you imagine that feeling? Do you want to feel that feeling? No. So when I start giving you things, be like, okay, I'm going to like kind of work my way through. Yes. It's usually at the beginning, so yeah, I don't know. We would have to look it up. It's on the AP Classroom, yeah, so you guys can look it up, okay? I am also happy to do like a tutorial session or whatever if you guys ever want one. On the other hand, I have been known to offer them, and it's like me here and nobody else. Do you know what I mean? So if you are interested, like I'll put up something on Teams, and if you're interested, you need to let me know, because I'm happy to run them, but I don't want to run them just for like nobody, you know, okay? Other than that, I'm just going to throw some AP Classroom stuff at you. I'm going to throw you some, you know how you got those review packages of free response questions? I'm going to give you some of those, especially because they have those, the chief readers reports that tell you what you need to be able to answer in each question. I also have like a full review of all the multiple choice questions, sorted out by section. Okay, and on Teams, hold on. On Teams, yes. So if we have a beaker that is like, if we have something that is like this, and it's actually worthwhile seeing this, even if you're not doing cell notation, because you might look at this and be like, oh my gosh, what on earth is happening here? Why do I have a platinum wire? And you're thinking, is the platinum going to be reduced? Is it going to be oxidized? If you don't know that it's an inert electrode that only is there so that the electrons can come down into the wire, right? And you got HCl in the solution. So, right, so the H plus, two H pluses can get together with two electrons. And when those get together, you get bubbles of H2. Yes? Now, could we have made the electrode out of hydrogen gas? No. Okay, normally what we would have as our cathode, you know, we might have copper, and we would have copper 2+, and we would have two electrons getting together with the copper 2+, and it would deposit onto the copper electrode, and you just have more copper. In this case, there's no way to make an electrode out of hydrogen, so we make the electrode out of something that can move the electrons down where they are in contact with the hydrogen. Does that make sense? I got one nod, two nods, 3, 4, okay. It works like that with graphite as well. The carbon is non-reactive and the electrons will just move through it. They'll make sure it's all lined up, you know, this way so that the electrons can flow that way. Yeah. Okay. And so this one, I wouldn't worry about the cell notation for this, though. If you're interested, you can look at it. We have our anode. We have our cathode. And then we have whatever's in the beaker. We have our magnesium 2+ ion, but over here we have H+, and we have H2 and potassium. You're not going to have to draw that. Does that make sense? Like, I'm not going to, but it's here if you ever have to, if you want to watch some videos on cell notation. The cell notation part itself there is not as important as knowing about the other thing. Gold is also inert. Okay? Platinum, gold, graphite, those are all inert. All right, and now we are going to move on to the standard hydrogen electrode on page 88. Yes? Yep. More like it's used enough by just this slot that makes it very expensive. Usually, yeah. Yeah. Okay, so we're going to be talking about the standard hydrogen electrode. This does come up on AP quite often. In terms of what you need to know for regular chem, you just need to know that it is the reaction that takes place in the middle of your reduction potentials chart. So if you could get out your pink sheet. All right. And if we look, we've got several gray lines. Yes, we got one at the top, we got one sort of middle top, middle bottom, and then one that's right in the middle. The one that is right in the middle is where we take 2 H pluses and add 2 electrons to make hydrogen gas. Does that remind you of anything we've seen extremely recently? Yes? What we were looking at a moment ago is we were looking at a standard hydrogen electrode, okay, where we had either platinum or carbon as the actual electrode itself, and then we had some HCl to provide the H+ ions, and we made H2 gas. Yes? Okay. Now there's a little bit more to it than that, but that's basically what it is. And if you'll notice, what is the reduction potential? Is 0. And what is the oxidation potential of the H2? 0. Is there any particular reason why we chose that particular electrode to be 0? Not really, other than the fact that it's kind of in the middle, and it is good as it works well as a standard. Okay? You could actually, if you wanted to, set a different reduction potential to 0. What would happen if we set a chromium half cell to 0? If we said, let's just, you know how Celsius 0 is where water freezes? Yes? And Fahrenheit 0 is like something like -32 Celsius? Yes? So 0 is in different places, just depending on how human beings happen to set it. Yeah? This 0 volts here works just like that. We happened as human beings to say, let's make this hydrogen electrode 0 volts. But did we have to have done that? Could we have said, oh, I don't want it to be that one. I would like chromium to be 0 volts in my other universe. Could we have done that? Yes. It would be awkward to do it now because everybody uses hydrogen as 0 volts. But if you remember, potential is all relative, right? The difference, I can get a positive difference between two negative values. I can get a positive difference between two positive values, or I can get a positive difference between a positive value and a negative value. It doesn't matter whether the numbers are positive or negative. The difference between them remains the same. Did that make sense? Yeah. Somebody had a question over here? No. Okay. So if I had set chromium to 0 volts, I'm going to put it in quotes because it's not, what would the potential of the standard hydrogen electrode be? Positive 0.74. So if you're ever asked a question like that, you just, recalibrate it to 0 and you say, okay, if this is 0, then the one below it would be negative 0.02 volts, and you just have to do a little math on that. Does that make sense? Yeah, if you set the reduction potential of, say, chromium to 0, then what would the potential of, let's say, manganese be? Because that one's too complicated. Let's say manganese here, and you'd be like, okay, what is the difference between 0.74 and 1.19, right? 0.74, 1.19. What did I do with my calculator? Yeah. 0.74, 1.19. The difference is 0.45. And so this would be negative 0.45 volts. Does that make sense? Okay. So not much to that. Let's go back to our standard hydrogen electrode then. Okay. And then I'm just babbling on here about the standard, having a standard as a reference and talking about the temperature, how Celsius is different from Fahrenheit. So just like 0 Celsius is not absolute 0, the E naught of the standard hydrogen electrode, which we call the She. So if we refer to it as the She, that just means the standard hydrogen electrode. That 0 is not an absolute value. It is a relative scale, which is what we were just talking about. Okay? All right. There is a video here that we are going to watch just so you can actually see what one looks like. I think this has an animation of one. Let's take a look and see. See if we've got sound and everything.
The standard hydrogen electrode is used to determine the standard electrode potential of a half cell. By definition, standard electrode potential is the voltage measured, or EMF we can say as well, when a half cell is connected to the standard hydrogen electrode.
So basically they found all of the other electrode potentials, reduction potentials, by attaching whatever that other half cell was, manganese or chromium or whatever, by attaching it to the standard hydrogen electrode and saying, what's the difference? Okay?
The standard hydrogen electrode is occasionally also called the standard hydrogen half cell. They're exactly the same thing. And for the most up-to-date version of any definitions mentioned in this video tutorial, please check out the video description, where you'll also find other links to further content from A-level chemistry. Let's take a look at what the standard hydrogen electrode is made of. Our apparatus needs to represent both sides of this equilibrium. To represent the H+ ions, we're going to use a 1 mole per decimeter cubed solution of hydrochloric acid.
Okay, this is British, so they don't use molar. They say 1 mole per decimeter cubed. A decimeter cubed is just a liter, so they mean 1 mole per liter, okay? I know, look at that unit they have to write instead of just capital M. How irritating.
The hydrogen gas we're going to use must be at 100 kilopascals of pressure and 298 Kelvin to maintain standard conditions.
Okay, so standard pressure is 100 kilopascals and 298 Kelvin. Now, when they say 100 kilopascals, I'm guessing that they actually mean 101.3, because that is the same as how many atmospheres? 1 atmosphere. Yeah? And I imagine that probably that little 1 atmosphere doesn't, or 1 kilopascal doesn't make that much difference. Okay?
Since there is no solid metal in the half equation, we must use a platinum electrode. Platinum is used because we need it to transfer electrons, and also it's selected because it's unreactive, we can say inert, so we don't need to worry about any alternative reactions taking place.
Oh, and by the way, this hydrogen here, basically what you would just have is you would either have some reaction generating hydrogen, and you would attach that reaction via a tube to here, and it would just like start putting hydrogen in. That seems unlikely though, because how are you going to control its temperature and pressure? I would imagine that you would just have a cylinder of hydrogen gas, you know, like an oxygen tank. Well, in this case, it would be a hydrogen tank. Yeah, so you know how you've got like cylinders of carbon dioxide, or like when people go diving, they'll have like a cylinder of air. Yeah, so it would just be like that, and you would, you know, control the pressure on a little pressure valve.
As mentioned before, the standard hydrogen half cell is the reference standard to which all other half cells are compared to. We have to do this because we are unable to measure the standard electrode potential of a half cell all by itself. So by defining the standard electrode potential of the hydrogen half cell as 0.00 volts, we can then compare the tendency of all other half cells to donate or accept electrons to the tendency of the standard hydrogen electrode, and then report this as a positive or negative voltage value. Let's look at some setups to explain this. For consistency, and to allow us to assemble an electrochemical series, the standard hydrogen electrode should always be placed on the left-hand side. This way, the sign and value of the reading on the voltmeter can be allocated as the standard electrode potential of the other half cell. This is the apparatus necessary to record the standard electrode potential of the copper half cell. Here you can see we have the standard hydrogen electrode on the left and the copper half cell on the right. The copper half cell represents both sides of its half equation equilibrium by having a copper solid metal electrode placed in a solution of copper 2 ions. The voltmeter, as you can see, reports a value of positive 0.34 volts, and this is then assigned as the standard electrode potential of the copper half cell redox system.
Okay, so who is the cathode and who is the anode here? The cathode is copper because it has a more positive reduction potential. So reduction occurs at the cathode. And so the one with the more positive reduction potential will be the cathode. The one with the more negative or less positive reduction potential will be the anode.
Now, with some further labels, we can actually see that this copper half cell is the cathode, the positive electrode, and the hydrogen half cell is the anode, the negative electrode. These roles can be allocated using the standard electrode potential values once we know them. Since we now know the half cell for the copper has a more positive standard electrode potential, we can understand that it has a greater tendency to accept electrons than that of the hydrogen half cell in this particular pairing. We could also say that the copper redox system position of equilibrium is further to the right than the hydrogens. Looking at...
Ooh, did you guys hear that? This equilibrium is further to the right than this one, which will be more to the left.
The very top labels, the direction of flow of electrons is from anode to cathode, aka negative electrode to positive electrode, and the salt bridge that we've got labeled up in the middle completes the circuit by transferring ions, not electrons. That's a common mistake. Next up, we have this apparatus for measuring the zinc redox system's standard electrode potential. So here are the half equations we need this time. Once again, we have a solid zinc electrode in a solution of zinc 2 ions as represented in the half equation in a very similar way to the copper half cell in the previous example. The standard hydrogen electrode is on the left, and this time our voltmeter reading is a negative 0.76 volts. This value and its sign is allocated as the standard electrode potential of the zinc redox system.
Okay, so in this case, who is the cathode and who is the anode? Hydrogen is the cathode and zinc is the anode because hydrogen has the higher reduction potential. Okay, very good. All right, we're almost done with this. Let's see if there's anything else
of the zinc redox system. The zinc half cell here with this final set of labels is actually clearly labeled as the anode this time. So that's different from the previous example, as we see a different direction of flow of electrons. The negative value on the zinc standard electrode potential informs us that the zinc position of equilibrium is actually further to the left than the redox system of the hydrogen, and that the zinc has a greater tendency, therefore, to donate electrons.
Okay, now here's a question that could be asked, and this is actually on the bottom of page 91. Okay, so if you want to go to page 91, we have a question at the bottom of the page. And this is something that could be asked on an AP exam, what happens to the pH near the platinum electrode as this particular cell operates? Have a discussion with your neighbors. And if you don't have a neighbor, you can turn around and talk with someone behind you maybe, or in front of you, or... And I'm going to call a name for this. So if you don't know, or the people near you don't know, go find someone who does. This is the wrong block. There we go. That's the wire. Nothing happens to the wire. What do you guys think? Are you ready? Okay. Juno. Since yeah, so you're going to have the equilibrium more to the right. This is our cathode. We're getting reduction. Yes? The concentration of hydrogen ions yeah, so our this is lying more to the right. We are actually forming bubbles of H2, and so the H plus is being used up, and so you have less H, and so the pH will increase. Okay? And it sort of explains that on the next page. Do you actually want to see pictures of like the construction of the She, or do you care? You want to see what it actually looks like? Yes. A little bit more? Okay, it's just 2 minutes. We probably won't watch the whole thing, but let's go take a look. Here we go. Oh, you know what? I don't have the links, so maybe you can watch them on your own if you want to. Yes? Because I haven't thrown up the links here. Okay. Cell potential. So yesterday we started looking at this, and I think you mostly got the hang of, did you mostly get the hang of how to find a cell voltage? Plus you had watched the video earlier. Okay. And you're good with finding oxidation potentials? Everyone's good with finding an oxidation potential? Anyone have a question about that? Yes? You're good? Okay, good. All right. Let's see. Given the following cell, so this is now on page 96. Given the following cell, what I would like you to do is I would like you to write the line notation for this cell and find the E naught of the cell using the two different methods. And by the two different methods, I mean E naught cell equals E naught of reduction at the cathode minus E naught reduction at the anode. Also using E naught cell is E naught reduction at the cathode plus E naught oxidation at the anode. You are doing example 5. Example 5.
So Ag is the
Yeah. Oh, cell notation. Yes. Yes. Sorry.
because that's an ion. The other one is like 0.34 minus no, you add the opposite one. You add the opposite one. So you do 0.0 plus negative 0.
Who's our cathode? Cathode is Ag. Do you guys agree? Yep. Okay, good. No, you don't. What am I doing? You write the anode on the left. And you write the cathode on the right. What would go in the middle here? The ions. We've got our ion sandwich, Cu2 plus.
Do you write the states as well? Or
Yes. So this should have a solid. Ag plus. Aqueous. There we go.
I think it should be one.
Should you choose this one or this one? The second one. Okay, because this oxidation will be, because this oxidation will be negative 0.34, which is higher than negative 0.54. You can basically say whichever one gives you the biggest distance between the two, if you're using a table like that, will be the one that you choose. Yeah.
32.
Oh, yeah.
For what?
Hi. Oh, thank you. Thank you. How do we feel about that? Is that good? Yes? Excellent. Okay. There's like a whole answer on the next page.
Wait, we did the calculation.
What did you do?
Yeah, we did the calculation wrong.
Yeah, they should both be the same. And it doesn't matter which method you use, but you should probably write the formula. Yes, you should write the formula so that, if you're writing on the AP exam, it's probably, this is the formula that they are probably most expecting you to use. It is the more common usage. So if you're choosing to do an oxidation potential, you should say, I'm using an oxidation potential. Yeah? Okay. And so this just gives you the answer. And then Hebden, should you use Hebden? Hebden makes me so mad because it gives the formula as E naught cell equals E naught reduction minus E naught oxidation and defines E naught oxidation as the reduction potential at the anode. And that just makes me want to cry. So I would ignore Hebden. Okay, so if you happen to be using Hebden as an extra study source, just ignore its calculation of E naught cell because it makes me like, how can you say it's an oxidation potential if it's a reduction potential? It just makes no sense. Yes? Okay, So I love Hebden, but that's the one thing I don't like. All right, so those are our cell potentials. And all of those cell potentials are at standard conditions. So ion concentrations are all 1 molar, and they are all at 25 degrees Celsius. And if you have a gas, it is at 101.3 kilopascals, which is 1 atmosphere. Let's just go with 1 atmosphere because AP works in atmospheres and it's an easy number to remember. Yes? Okay. What if we're not at standard conditions? Oh, ho, ho, ho. Now, let's just take a quick look here. Let's say we had, I don't know, let's just do lead and zinc because they're really close to one another, okay? So let's take a look at lead and zinc, and we're going to be talking about how we get closer and closer to equilibrium, yes? So if we have lead here, and we have, let's just do lead and we'll do cobalt because cobalt is right next, it's nearby. So we've got lead and we've got cobalt. Originally, your cell voltage, your initial cell voltage is going to be is going to be 0.28 minus 0.13, which is 0.15 volts. Now, as time goes on, what is going to happen to the concentration of lead? Lead 2 plus. It's going to decrease, yes? Because in an electrochemical, in a galvanic cell, I don't know if this is helpful to you at all. This is how I did it when I was in high school. I was always like, oh, okay, an electrochemical cell goes like this. We get energy out, and then it goes like that. So I don't know if that's helpful to you, but that's how I always thought about electrochemical cells, is that the top reaction goes forward and the bottom reaction goes backward. Hi. Now, as this reaction proceeds, the concentration of lead is going to decrease. So what's going to happen to the forward rate? It's going to decrease. So what's going to happen to the potential to go forward? It's going to decrease. So as the lead concentration goes down, the E naught of reduction is going to go down, right? So these are going to get closer together, yes? Right, so you can imagine that lead might be now down here somewhere, okay? After some time has gone by. And then with our cobalt, as time goes on, what is happening to the concentration of cobalt? It's going up. So which direction is that going to push that equilibrium? It's going to push it to the, if this increases, it's going to push it to the right, yes? So what that means is that the potential, if it's pushing it to the right, the potential to go forwards is actually higher, yes? So this number is going to get higher. So the cobalt is now going to be up here. So now you're going to have a potential that is a potential difference that is smaller, yes? Until eventually they come together in the middle, and that's when you reach equilibrium. And when they are at equilibrium, the difference between the two is 0, and it's due to those changes in concentration. Yes? Okay. So let's go here. Yes?
So the potential, it's like kind of similar to just the rates, right?
Yeah, exactly. So as time goes on, those two rates are, yeah, they are becoming the same. Okay. So at non-standard conditions, so that means we are not at 1 atmosphere. So standard is 1 molar, 25 degrees, 1 atmosphere. Here's our battery in standard state. We just talked about why the cell potential becomes 0. When the reaction is at equilibrium, there is no net change in the amount of zinc or copper. No electrons flow. The cell can no longer do electron work. This is on page 104. Is that an ionic compound? Oh. So when a cell is equilibrium, E naught equals 0. We just talked about that. I feel like I did a better explanation just off the cuff rather than what I've written here. But if the cell conditions are not standard, but the cell is not at equilibrium, what do we get? You will not have to calculate the voltage at standard conditions for the AP exam. However, you should be able to determine whether a cell potential is greater than, less than, or the same as standard conditions when the conditions are changed. Let's just go take a quick look at the data sheet for AP. They actually do give you the tool to calculate it should you so desire. So at non-standard conditions, you can use this formula here to calculate the potential at non-standard conditions. You're not expected to use that formula, but they give it to you. So you are welcome to use it should you so desire. Yes? So this is the cell potential at non-standard conditions. Yes? Okay. That's a very good question. Now, N is the number of moles. T is temperature. What is R? You guys should know R. R is the gas constant. Okay, so R, now do they give you R here or do you have to go searching for R? Oh, they tell you R is the gas constant, but they don't tell you its value over here. Okay, so the nice thing about this is that you're like, oh my gosh, what are all these letters? Well, it tells you what they all are there. Does it give you N? Yes, it does. N is the number of moles of electrons. Okay, it tells you that F is Faraday's constant, which is this value here. Yes. And it tells you that T is temperature. Probably. Yes, it does. So in theory, you could do all of these things. And then what do you imagine Q is? Is the concentration of the products over the concentration of the reactants. Yes? So it's just a Q like we used in KEQ calculations. Yes? So you'll take your concentration of your products, whatever is given to you in the question, and divide by your concentration of your reactants. So if you're stuck and you're like, I don't know how to explain this very well, you can always fall back on math. to be like, it's going to be smaller because watch me do the calculation. Yes? However, like I said, they don't expect you to be able to do that. So what do they expect you to be able to do? So for an electrochemical cell, a galvanic cell, K is very large. That's why that reaction just trundles along to completion, right? That's why the battery just keeps going until the battery dies. Yes? So K is large. In other words, the concentration of the products is much, much bigger than the concentration of the reactants. Yes? When a system is at equilibrium, Q is equal to K. So when we're okay. I said that poorly. When we are at equilibrium, right? Because this is at equilibrium. Yes. Does it make sense that the concentration of the products is going to be really big because your battery has died? You have used up all the reactants and you have mostly products left? Yes? So the system is at equilibrium when Q is equal to K. So when we have actually reached equilibrium, the voltage is going to be 0. So since K is very large, if we have Q values that are larger, that means that we are closer to K. Does that make sense? So the bigger the amount of product is, the closer we're going to get to K, right? The smaller the amount of reactants is, the closer we get to K. As a cell approaches equilibrium, what happens to the voltage? The voltage gets smaller. So if we have had an increase in product, so let's say we've made an electrochemical cell, and instead of making it at 1 molar for who produces ions? The anode produces ions. So say for the anode, instead of having 1 molar in there, I've added 2 molar, yeah, of my ions. So I've got lots of product. Q is going to be, if I have lots of product, Q is going to be larger. And so are we closer to or further from equilibrium? We are closer to equilibrium, and therefore the E naught of the cell will get smaller. If we decrease the concentration of a product, what's going to happen to Q? Q is going to get smaller. And remember, K is big. K is big. So are we getting closer to or further from equilibrium? We're getting further from equilibrium, and the E naught cell will get larger. Okay, we'll talk more about this next day. I'll put your homework up online. I'll also put it up here, but you don't have to stay for it. Okay? Yes.
First off, where does the K plus ion go?
Cations go towards the,
cathode,
yes. Anions go towards the anode.
but then we also have CO2 plus, right?
And it also goes towards the cathode.
So,
Thank you.
so this would be like,
Well, no, because that you're saying it's the negative ions are migrating towards copper and aluminum. So you said it migrates towards both electrodes.
would it not consider it?
No, it says towards which electrode?
Oh,
Yes? Yes.
But
Yes.
would any of this like work if there was more than 2 beakers or just
Just 2 beakers. We can actually have 3 beakers in some cases, but
which
yeah.
case?
like,
Which case?
Let- Yeah. Let's see, just have them.
So I was not off. Yo.
I
This
don't like
might
think-
be my.
I don't
only
like
s-
thinking about them.
This might
they
be my
won't-
only stupid idea that actually works. Right? Like when you were doing the hydrogen thing and
Uh-huh.
what? I put another one. Did we ever get that on the test?
Do you know what? You can actually, okay, so here's what can happen. You can have an electrochemical cell powering an electrolytic cell, which is the one that goes backwards, which is non-spontaneous. So this one is spontaneous. This is like attaching a battery to a non-spontaneous cell and making it run. Okay, so that's the only time when you would have 3 beakers.
It's basically like using the charge.
Yeah, using this to make these electrons flow the correct direction. Yeah.
By technicality, that's not 3
Not coming
galvanics.
up.
No, it's not 3 beakers in a galvanic cell. It's
3?
3 beakers, but yeah. Yeah. I knew I'd seen one somewhere. Yeah. Yeah.
This is peak. I feel like. Also, how do you know if it's CO2 plus or just CO2?
Which one has
Like when
the
you're doing
better potential? Which one has the bigger potential?
It's CO2 plus.
Yes. That's why it's CU2 plus.